Today we will be looking into transformation of quadratic equations. Quadratic equations have three components: a value, b value, and c value. We will specifically focus on the changes happening with the a and c values. We will take the parent function and we will make changes to a and c values, and we will see what those changes are reflecting on the graph. In general, a value will tell us to stretch, compress, and or flip the line, just like we have done in linear transformations. The existence of b value showed that there was a horizontal shift. We will focus on that next class. Lastly, the c value will tell us the y-intercept, not necessarily how many units has been shifted up or down, it's just going to be telling us the y-intercept. Let's remember a little bit about the quadratic functions. The most basic quadratic function is y is equal to x squared. That's the parent quadratic function. On every quadratic function, we have a vertex, which is lowest or the highest point, and we have an axis of symmetry, which divides the parabola into two parts where one is symmetrical by the other. Let's graph some points on the parent function. Let's start with -2, -1, 0, 1, 2, 3. Y values, if we plug in -2 into y is equal to x squared, we can find the y values 4, 1, 0, 1, 4, 9. So let's graph these on the coordinate plane as well. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. Because we know the parabola is symmetric by the axis of symmetry, I know that there's going to be a -3, 9 in here as well, just so that we have a nice graph here. Our parent function is going to be passing through these points. Now, let's look into the next example and then compare the changes with the parent function. In this one, let's use the same numbers, and we will be substituting these x values into the y values so we can actually compare the results. When I plug in -2 inside of the y is equal to 2x squared, y value should be 8, 2, 0, 2, 8, 18. Let's graph these as best as we can. -2, positive 8, -1, positive 2, 0, 0, 1, 2, 2, 8. 318 is not going to fit. So if we graph our new function, it's going to look like this. We can clearly see that the new function is more narrower than the parent function. It got more narrower. We can see the differences by comparing the vertical stretch or compression. When I look at the y values here, y value for 1 is 1 on the original. In the second one, y value goes to 2. When x is 1, y is 2. On the parent function, when x is 2, y is 4. On the new one, when x is 2, y is 8. Compare these y values, 1 to 2, 4 to 8, we can see that y values are being vertically stretched. So because the a value is greater than 1, we have a vertical stretch to our parent function. Let's look at another one. This time it has a fraction. I'll have the same numbers in here, -2, -1, 0, 1, 2, 3. We don't have to have these numbers. I just choose those so that it will fit in our some tiny graph here. You could use any number in here. When x is negative 2, y will be 2. When x is negative 1, y would be half, 0, half, 2, 4.5. Let's graph these. X is 1 and x is negative 2, y is 2. Negative 1.5 as best as we can. 0, 0. Here's the half. And 2, 2. 3, 4.5. It looks like our graph is going to be passing through these points like this. And it's kind of hard to see the comparison with the parent function without graphing the parent function. So let's graph the parent function at the same time. On the parent function, we have 1, 1, 2, 4, 3, 9. And negative 1, 1, negative 2, 4, negative 3, 9. Comparison of the new one and the old one shows us that the y values are being compressed. And when I compare the y values here, for example, instead of going to 4, we go down to 2. Instead of going to 9, we're going down to 4.5. So there is a vertical compression. By 1/2. Now, our parabola opens up. Our vertex is 0, 0. We can write those. Axis of symmetry, x is equal to 0 line, or you can write y-axis. What has changed? The a value. If a is greater than 1, graph is stretched. If a is less than 1, the graph is compressed. The role of a is to tell us whether to stretch or compress. So vertically stretch or compression. Let's look at another example. Let's make this an x squared first. Y is equal to negative x squared. Let's select some points. Negative 2, negative 1, 0, 1, 2, 3. Let's evaluate these x's in the function to find the y values. Negative 4, negative 1, 0, negative 1, negative 4, negative 9. Let's graph each of these points. Now, when compared to the parent function, it looks like this function is going to pass through here, all of these points, and continue. And when compared to the parent function, this function opens down. Vertex is 0, 0. Axis of symmetry is x is equal to 0 line or y-axis. What has changed? The a value. In addition, if a value is greater than 0, the graph opens up. And if a value is less than 0, meaning negative, then the graph opens down. The sign of a tells us to whether to reflect over the x-axis or not. Let's look at one last one here. I will start with my numbers, -2, -1, 0, 1, 2, 3. Let's plug in our x values so we can find the y values. Y is 6, 3, 2, 3, 6, 11. Let's plug these in the graph. -2, 6, -1, 3, 0, 2. These are our points. If I want to try the 311, 311 would be right here, and its reflection should be right here because it's symmetric. I can create my graph by connecting the dots. Now we can answer our questions. Compare with the parent function. This parabola opens up just like the parent function. There is no reflection because it's still opening up. There is no vertical stretch or compression because a value is equal to 1. If a would be greater than 1, vertical stretch. A is less than 1, vertical compression. Our vertex has changed to 0, 2. What has changed when compared to parent function? The c value has changed. And c value also gives us the y-intercept. And we can also realize that every point on the graph was shifted, translated 2 units up. And role of C is to finding the y-intercept. And if y-intercept is same as the vertex, then C also gives us the translation. Role of C is to give us the y-intercept value, and if y-intercept is same as the vertex, then y-intercept can also give us the translation amount. We will translate these parent functions with the vertex. If the vertex is shifted, then I know there's a shift, then we can know there's a translation. That's pretty much it. In the class, we will go into a little bit more detail.